Okay, now let's solve this problem that we have solved by using bisection method. So remember the bisection methods. We choose an interval, then we find the middle point of it, and we check its value, because we are looking for a value which is closer to the 0, and then we continue like this. So at each step we get closer and closer to the bisection method. And in fact here we have the Poseidon code for it. So let's analyze the Poseidon code. We begin with the iteration 0. So first we have the root xr for the function, and we have a dummy variable, so xr is assigned to xr old. Then xr is changed as half of the lower and upper bound. Then we increase the iteration 1. If xr is different than 0, then we check the relative error, okay, because this is what we are looking for. So here x is the value of the function. Maybe it's better to say that instead of x we say that y. So because that is where we are looking for, and the corresponding x value for that. If the relative error is smaller than some value, so if xr is not 0, otherwise it's not at the origin, then we calculate the relative error. This is done in order to avoid the underflow. Okay, so then we check the whether lower and new fxr values are positive or not. If it is negative, then upper bound is modified with the xr. If it is positive, lower bound is modified, and otherwise else, then the error is 0. We say that's okay. If the approximation error is smaller than the specified error, or the number of iterations are higher than some certain value, we say that exit. And of course then the bisection, the root is equal to xr. So this is how we find. Okay, so let's write the code in MATLAB. Again, we will begin with new script. We say that function MECH310 bisection. Okay, now we need to define the upper and lower bound, okay, for the root. This is the first step. So remember from the previous problem, our lower bound is 4 and our upper bound is 20. That's okay. Now next step is we will evaluate the function for these values. Okay, so let's say that f lower is equal to my function xl okay. Then I have the upper bound, function of the fu, my function xu. Okay, now if L and Fu is defined, now what I'm going to do next is the check whether this is negative or positive, because I want the lower and upper bounds, the values for the lower and upper bounds on either side, right? So first I need to check whether it's negative or positive, because we have some pitfalls, right? And this is the function that I want to find the root. Okay, now let's do something else before writing the test. I have to define the fr. Now I need to define an inside the loop. I have to define an fr. So basically what I need to do is, first I put a for loop and end. Now I may give an estimate for the number of iterations. Let's say that I have an estimate of 20, so within 20 iterations it will reach to the root. Now what I need to do is first find the new point xr. Certainly xr is equal to xl lower bound plus upper bound divided by 2. Now what I'm going to do is I will evaluate my function at this new point. So let's say that this is fr. Okay, now I evaluate my function fr. Now let's check, let's see my Poseidon code again. Okay, so what it tells me is, first I will check the lower bound. So if fxl and fxr is smaller than 0, then set xu is equal to xr, and then go to step 2. Now I will put here an if comment, but first I will test. I will define a dummy variable test. I may not do it, but just do it. Test is equal to fl multiplied by fr. If test is negative, this is end. Let's see what the Poseidon code tells me. If xl multiplied by xr is negative, then xu is equal to xr. xu is equal to xr. That's okay. Now I have a second condition. If xl multiplied by xr is positive, So else if sorry, this was negative, huh? If test was negative, this is what I'm going to have. If test is positive, then XL is equal to XR. Then go to the step 2. What was step 2? XR is equal to XL plus XU, and you evaluate the functions again and again. And if it's equal to 0, XL multiplied by FXR is equal to 0, which means that either the FXL is 0 or FXR is 0, exit. So let's write it here. And let me check whether there is something called exit. Okay, I say that exit. Help on exit. Yes. Exit terminates the current session of MATLAB. This function is equivalent to the quit function and takes the same options. For more information, see quit. So this is what is written, and let's check the quit then, because I want to know how it works. Quit terminates the MATLAB program. Quit function does not automatically save the workspace. To interrupt the MATLAB command, see stop execution. Quit code force bypasses code, exit code, and let's see the examples. Okay, maybe it's not a proper choice, so let's do it like this. I need a comment alternative to the for. So let's look at the help of for, whether I can put a conditional statement on for. Now again, I will open it. I will open the help menu. Let me enlarge it. Okay, so remember that I was able to put steps. Oh well, we learned something. I can define certain values for the for command. Extended break, colon, continue, return. Here is the break. So let's see how it works. Break terminates the execution for or while loop statements. After the break statement do not execute in nested loops. Break exits only from the loop in which it occurs. Control passes to the statement that follows the end of the loop. Let's see the examples. Well, we learned something. There is something called while. So, okay, so it looks like this, huh? If some variable is bigger than limit, it breaks. So it stops the iteration. Okay, I can use it, but there is something called while. So else it's break. Now the point is this here. I can evaluate the function before the loop or inside the loop. Let's say that this is itermax then. And let me define another variable here, itermax, maximum iteration. And it will be increased one by one. Of course, I have the dummy iteration variable index. So I say that index is equal to 0, and then well, sorry, not in this case. I don't need to define the index. So I have my fr, but certainly I need to define the value for lower bound. So xu is equal to xr, xl is equal to xr. Let me check my Poseidon code again, how it works. So method tells me something. Okay, choose the xl and upper bound. Okay, estimate the root determined by xl and xu divided by 2. Yes, it will be somewhere in between. Make the following evaluations to determine which subinterval the root lies. Fxl multiplied by fxr, the root lies in the lower subinterval. Yes. Therefore, xu is equal to xr and return to step 2. Yes. If fxl multiplied by fxr is bigger than then set fxl equal to xr. So when I evaluate the fxl equal to xr, I have to evaluate the fxl here. Okay. Maybe it's better to write here instead of fxr fxu and modify the code a little bit. Okay, so this is fxu. So what I'm going to do is here I will just copy these lines because now I modified the fxu. So I want to evaluate fxu here. Okay, and then fxl here because I changed the values. That's also okay. Now what I'm going to do is I will change the test function. Instead of writing here fxr, because I don't need to evaluate it anymore, okay, yes, because I update the fxu here, yes. So this will be fxu, let Let me check, maybe there is a problem. Okay, so let's try to look at the value for the XR and what will be at the end, because we roughly know the value of XR. And let's run the script because it's getting complicated. Yes. Okay, so line for ethermax is undefined. Yes, we didn't define the ethermax. Let's say that it is 10. It seems that our code is working. So now we have the new root, and let's find the index value for XR. Whether it is run within the 14 point. So let's check the error and relative error also. But first open my function. I will open my function. Okay, because I forgot to put a semicolon here, so it writes the results every time on the window. Now let me continue. I write the script. Okay, so each time you see, this is one methodology, and let's here before the break, because when test is equal to 0, it is just on the root. And let's check. Okay, so index is not seen here. It doesn't go to this command. Let's debug the code, maybe that's better. First I will put a breakpoint here. I will run it. Now I'm inside the loop. First XR is computed, then FR is computed. I will not get into the my function, so FR is get it here. Now test is evaluated. Let's check the test value. It's a positive value, 209. Okay, so if test is negative, no, test is positive, then it gives us XL is equal to XR. Now I have the FL, then end, then it goes to the again. Now I have the new XR, so let's check. XL is 12, XR is 12, XU is 20. Now I have a new XR, it's 16. I have new FR value minus. Now I check it from the right hand side. Now the test function is negative. XU is equal to XR. Now I have the F of U. It goes to the end. Now I will do the next iteration. Again I will check the test. I'm just debugging it and seeing how the results are. Now test is positive, you see. Else if XLR and it goes like this. Again, I'm checking the test now. You see FR and FU is getting closer and closer to the zero, as you see from the workspace. Now the test value is getting closer to the zero. And it goes like this. Okay, so basically it runs all the iteration. This means that it never goes to the test and FL is never becomes zero. This is very typical, but this is just for a condition. So this means that I need another termination criteria. Fine. So let's do something. Now I have the next XR. Now I will define another variable, XR previous. And that's equal to XR. Now I have I need a new stopping criteria. Let's put a semicolon here. I forgot to put it. Now let's calculate the previous one, the relative fractional error, with the new one. So EA, let's say this is the relative fractional error. So remember that it is the absolute value of XR minus XR previous divided by XR multiplied by 100. So if now I need a stopping criteria. ES is the specified error. So let's say that 0.01. I just put a value which is small enough. Of course, we have seen how we can determine the machine epsilon. You can put such kind of a value there as well, but in general we don't do it like that. So this is my error. Now if EA, so EA is a positive number smaller than ES, this is end, this is break. So normally it should get out of the do loop. And let's check whether it will work or not. First I exit the debug mode. So here I put the iter max 100, so sufficiently large value now, and I run it. Oops. At 9. Okay, so I haven't defined the value for XR yet, so I cannot define it here, what it tells to me. So in order to avoid this confusion, let's take this line out of the loop and see whether it will work or not. No, I cannot. So what I need to do is I will take this line here and we'll put it here. Now XR will be X previous, and then it will come here. New XR value will be calculated. Then it will calculate the error. Let's put a breakpoint here and let's check whether it will be okay or not. Now I don't have the XR previous, so again it will make an error. Okay, so I have to define an XR previous outside the loop. So just put a dummy variable here and let's say that this is 0. It will not make any mistake. So basically for the first iteration, if I do it like this, my first error will be 100%. So it's okay. Again, let me run it. Let's check the EA. You see my relative approximation error is 100% now. Okay, let's go further. Okay, so EA is bigger than ES and it doesn't run this line anymore. Now when I come to this line, now XR is 12 but X previous is 0, so I go further. Now it will calculate the relative error EA. EA is calculated. You see now it is 25%. That's okay. Still it is bigger than the step size. I continue further. Now look, XR previous is 16, XR is 16, and I will go to the next step. Now let's check the EA. You see the next error is 14.28 and it goes down. Let me check the error. Okay, it is 6.6% now. It's going down. Okay, so now at this point I will remove the breakpoint and press the continue button. Okay, Now I have a root 14.8011. So let me put index here, and I want to learn whether it runs until the maximum iteration number. No, it reaches this value at an index of 21. So let's plot it. Let's plot the error. Okay, so error is, I will index, error index is equal to EA. That's okay. Now root value is another index, another parameter, index, and that's equal to XR. And let's plot it instead of using such kind of a variable. Now I can remove this line from here. I don't need it anymore. It seems that my code is working properly. So I write figure plot. I don't need to write X variable. You can check it from the help of the MATLAB. So here I write plot error. Now my second one is figure plot root value. Okay, I will run them. You see? So as you see, so the horizontal axis is the iteration number, and we don't have the zero iteration. It begins from 1, so it begins from 12, and in the first iteration it goes to 16, and then it comes to 14, and then it slowly converts, then 15, 14.5, and so on, and then it reaches a certain value, as you see. So it converts after certain number of iterations. So basically we can say that after 10 iterations, or let's say roughly somewhere here, it converts. So this is the root value, how the root in bisection method evolves with the iterations. Okay, let's check the error. This is my graph for the error. Of course, you see that it is exponentially decaying, okay, and it's not very clear what's going on after 10. Now let's check the properties of the plot command. So help on plot. Okay, so it's a 2D line plot. You can define the line specifications. You can define XY plot. I want to see how we can define the line specifications. So here it gives an example. X is defined, Y is defined, and then it says plot XY. So that's okay. We have done it. You can plot multiple functions in a single plot command. We will have a look at that, but this is not what I'm interested in now. What I want to see is how I can define the lines, whether there exist any examples. Okay, so here you see you can define the lines whether they are dashed or not. So here is an example. Well, for example, one line is defined, xy2 is defined blue with O dots, and xy1 is defined with the green, sorry, G is for green, and C is for central. Anyway, so marker indices, and so on. So there is P. You can play with the line width. You can line space, plot, anything. Yeah, here X label and Y label. This is what I have been looking for. I copy these lines. So I put it here. Title. Relative approximate error. X label is the iteration, and Y label is the error. Okay, now let me copy these lines because I need the titles also for the other one. So value of the root, X label is sorry. So this is the value, and the other one is the iteration. Yes, but still a problem. I mean, because I need something else instead of plot. It's not clear for the very low plots. Let's look off to the help whether is there something that I can make the scaling. So there are lots of options. X label, Y label, button plot, and so on. Plot. You can change the line specifications and many other things. Here are the descriptions for the markers. Okay, O is for circle, plus is for plus sign, and so on. You can find the color specifications here. Okay, and other things, line style specifications. Well, there's lots of things. I mean, you can examine by yourself, but this is not what I'm interested in. Whether I can plot it, here it is. I have other options, so GCA, hold, legend, log, plot tree, title, X label, X limit. Whether I have a log plot, what's a log plot then? Okay, so now this is what I can use. You see, log plot plots X and Y coordinates based on the logarithmic scale. So this is what I need. And the command is log. Now I modify this line. Now I run it. I will wait for a while. Okay. Now here it comes. Now I have the iteration. So I have the X label. I have the Y label. I know now the title of the figure, value of the root, and let's see how it changes. What's a log plot? Okay, now here it comes what the log plot is. So 10 to the power 2 is 100. Now you see how it decreases. So it is, remember the value that we put as a stopping criteria, 10 to the power minus 4, and here it is 10th iteration. So it is, the error is somewhere here. Okay, it is 0.1% approximately. You see, X is equal to 8 and Y is equal to 0.42, and it goes like this: 9, 21, 10, you see, 17, Y value is the error. So this is relative approximate error. Okay, so this is how you can write a script for the bisection method.